Well, good afternoon. So as we start today, first let me just note that I have your new homework set for the week. So these problems are this week's material, all due next Wednesday. Remember that you have, about 7 or so, 8 problems from last week that are due on Wednesday, so don't forget to bring that with you. And I have some old homework to be picked up here as well. Just a note or two on the homework that you're doing now. One student had asked a question just a minute ago, and I thought I'd answer for all of you. If you have a mixing chamber, then in a typical mixing chamber, the pressure is going to be the same everywhere in the mixing chamber. Think of a mixing chamber just like a big open container with 2 pipes coming in and 1 pipe going out. There's really no possible way for the pressures to be different in any of those particular fluid streams. If, let's say, the discharge pressure were less than the inlet pressure, then the fluid would be pushing back upstream and up those inlet pipes, right? You have to have the same pressure in each section of a mixing chamber. So when you're looking at, there was one homework problem that dealt with mixing chambers. It doesn't specifically tell you that the outlet pressure is the same as the 2 inlet pressures, but that's really what they're applying. So please make sure that you recognize that the 2 inlet and exit pressures are always going to be the same for a mixing chamber, unless you're told otherwise. But for most problems, they will always be exactly the same. Let me also remind you that I had reassigned problem 32 from the previous homework set to the homework set that's due on Wednesday. And remember that to solve that one, you need 2 simultaneous equations. You'll have your mass flow rate equation, which you'll combine with your ideal gas equation of state, and that'll give you 1 equation in terms of the unknown temperature and velocity. And then you'll have a second equation, which is just your first law of thermodynamics, which will also have an unknown temperature and velocity. So 2 equations solve for 2 unknowns. So that's the hint that I gave you a week ago, but I'll just give it to you again because it was arguably a somewhat confusing problem. Anyway, let's just move on to new material now. One other thing I wanted to mention. I've been updating Blackboard, so I think we're up through lecture number 13 now that's available as a recording on Blackboard. Also, I've included all the example problems that I'm going to be working on, the ones we've already done, but also the ones that you'll see over the next month or so. I really never thought to make these available to you until some students were saying that it's kind of hard to read the problem that's on one board and my lecture that's on the other board up here, and this way you should all have access. So I put those up just right before class today. They're all in image format, so you should be able to access the image on your smartphone or your iPad or anything you bring with you to class. As long as you can access Blackboard, then just go to course information, and there's a new topic there that's called example problems. So they're all shown there. Again, they're all images. So anyway, moving on. So we're actually done, believe it or not, with the steady flow problems associated with the first law of thermodynamics for an open system. And we're going to move on now and talk about another type of problem, which we call uniform flow problems. By the way, another thing that I learned last time afterwards was that some students are having trouble just reading the writing that I have just because the thickness of the pen was not really that thick. Again, I didn't realize that was a problem. I guess it's more of an issue once we have one board going to the computer and then the other board is just a lecture. Those of you sitting over here probably have some difficulty reading over here. So I'm using a thicker pen starting today, and hopefully that'll make it easier for you to read the material that's going up on the board. All right, so uniform flow. First of all, we're still talking about processes involving the first law for a control volume, or an open system, if you will, but we're no longer talking about steady flow problems. And there's a couple of main differences between the uniform flow and the steady flow problems. So first, one difference is that the state will actually change inside the control volume. And again, I'm just going to use CV as an abbreviation for control volume. Okay. Although it remains uniform throughout the control volume. So the state will change inside the control volume, but is uniform throughout. Then the other difference is that the state of the entering or exiting substance is going to remain constant, but the flow rate will vary. The state of the inlet and exit remains constant. But the flow rate, I'll write this as m dot, but the mass flow rate varies. Okay, so this is a little bit different than our steady flow problem, and the types of problems that we're going to use this method for are also going to be different. These types of problems are typically used for filling or for emptying a vessel, like if we're discharging the fire extinguisher or if we're filling up our propane tank down at the U-Haul store. Those would be kind of typical of these particular types of problems. So again, these are primarily used for filling or emptying vessels. We often call these charging or discharging problems. So these are called charging or discharging problems. And what I'm going to do is look both at the continuity equation as well as our first law and modify them from the general form to be more accommodating of these types of problems. So let's just move on with that. All right, so first things first. Let's just remember the continuity equation. And the continuity equation basically tells us that the change in the control volume mass with respect to time is just going to equal the difference between the rate that mass flows in, so that's the sum of all inlet streams, m dot I, less the rate that the mass flows out. So that's the sum over all exit streams of m dot d he. Now this could be written in different ways. Sometimes we put the two terms on the right-hand side over onto the left-hand side of the equation, but I mean this should make sense to you, right? The difference between what enters and exits is what remains, right? So if the entering flow streams have a greater mass than the exiting, like let's say you're filling up the propane tank, then the change in the mass of the control volume will be positive. If we're emptying the propane tank, then the mass that leaves is greater than that which comes in, and we have a net reduction in the mass of the control volume. So this is one term that we're going to note, or one equation we're going to note, but let's also, again, keep in mind what it says above. The mass flow rates will vary. You are definitely going to have a different rate that mass is going to flow in versus what flows out. And in fact, in many problems, we're going to have nothing flowing in or nothing flowing out. Again, if we're talking about like filling up a propane tank, you don't empty the propane tank while you're filling it. We're talking about a fire extinguisher being discharged. You're not filling it while you're discharging it. So it's very easy for one or more of these terms to go to zero, and we'll talk about that here shortly. Anyway, if we take this continuity equation and now just integrate over time, then basically the dmdt term for the control volume, well, that you differentiate that and you just get the mass. So the mass evaluated between the initial and final state is just going to be m2 minus m1. So that's what we get on the left-hand side of the equation. And on the right-hand side of the equation, remember the dot represents the time derivative. So if we're integrating over time, then we're getting rid of the time in the denominator, and we just end up then with the sum over all exit streams of ME minus the sum over all inlet streams of MI. And note that I and E and 1 and 2 are not the same things, okay? Unlike the single stream steady flow problems where I've replaced I with a 1 and E with a 2, here they mean different things, right? Here, 1 and 2 represent, the final and initial state in the control volume, yet the I and the E represents what's entering or exiting, right? So E represents what's flowing out of the control volume, and I represents what's going into the control volume. So no more equating 1 and I, 2 and E. They're different now. Anyway, here is essentially a version of the continuity equation that we're going to use for these types of problems. Let's now look at the first law. If we look at the first law, and I'll just write this in, well, a very general form, we would get that the rate of heat transfer plus the sum over all inlet flow paths of m dot I, and then hi plus di squared over 2 plus gzi. And these are all i's here. This is going to equal the rate change in the energy of the control volume. And remember, this term would have gone away if we're talking about a steady flow process, because for the steady flow process there is no change within the control volume, but now there is a change in the control volume. I mean, we're always uniform throughout the control volume, but it's still changing over time. So there is a change in energy over time with respect to the, well, for the control volume itself. And then we also have the exit terms, so the sum over all exit flow paths m dot E, and then HE plus DE squared over 2 plus GCE. And then we add to that the rate of the work of the control volume. So this is the general form of the first law. Again, it's not the single stream steady flow, it's not the steady flow, it's just the general flow. So now what I'd like to do is just make a note. So if we're looking at the control volume, the energy associated with the control volume is, well, we've seen the definition of energy. Energy is going to be the internal energy plus the kinetic energy. So let's write this as MV is going to be 2 plus the potential energy. So I'll just write that as GZ, I'm sorry, mGZ. So this can be rewritten as the mass times the internal energy, I'm sorry, specific internal energy, and then plus V squared over 2 plus GZ. And then what I would like to do is I would like to differentiate this. I mean, after all, this is going to have to go back into the first law equation above. So if we take the change in energy with respect to time for that control volume, now this is in d by dt of mass. Then we have the internal energy plus kinetic plus potential. Well, at this point, what I'm going to do is kind of a couple of steps all at once. I'm going to go back to my first law equation, but now I'm going to integrate the first law, and we'll do it over time. So we just go back up to the equation above here. I'm just looking at this whole equation here. And let's take that and integrate it over time. Note that as I do this, at the same time, I'm going to be plugging in this equation that's directly above. So this equation goes in up here, but then it too gets integrated. So I just want to make sure that you're aware of that. So let's integrate the first law over time. And let's just be sure to include the equation above. So if we do so, what are we going to get? So let's just take these one term at a time. First of all, the integration of Q dot over time, well, that's just Q, right? I mean, Q dot is dQ dt. If we integrate dQ dt, we just get Q again. So that's just heat transfer to control volume. if we integrate the next term, keep in mind that for these uniform flow problems, there is no change in the state at the inlet or at the exit. Whatever it is at the beginning of the problem is the same as it is at the end of the problem. So there's no change in any of these terms, right? There's no change in the enthalpy, the velocity, the height. The state is the same. The only thing that then integrates is just the mass flow rate term. Remember, the mass flow rate is really dMdt, so if we integrate that, then we just get the mass again. So this summation then just becomes the sum over all inlet streams of mi, note that the dot is gone here again, and then times hi plus vi squared over 2 plus gzi. And then on the right-hand side, well, here we're going to have to be a little bit careful. First of all, I don't have a lot of room, so I'm going to move down to the next line. But here, we're looking at the dEdt term, right? So we're integrating that. Well, if we integrate that, again, this is a dt. The integral just becomes the mass times the internal energy plus the kinetic and potential energy. And we have to evaluate that between points 1 and 2. So what we get here then is m2 and then v2 plus v2 squared over 2 plus gz2. And then minus m1, v1, oops, that's not supposed to be I, that's v1, plus v1 squared over 2, plus gz1. So that's the change in the internal energy of the control volume integrated over time. Okay? And then we have to add to it the integral of the exit term. So again, this is one long equation, but I have to keep spreading it down here. So next, we would have the sum over all exit streams of the mass at the exit and the enthalpy at the exit plus v squared over 2 plus g the exit. And then last but not least, we have the work term, the w dot term. Again, we integrate that, we just get w, so plus w. So this long equation right here is the first law for uniform flow. Now, as you're looking at this equation, you realize, there's only like 18 separate terms, so how hard can that be to solve the problem, right? Obviously, I'm being facetious. We don't have problems that use this entire equation. What we typically do is simplify this into problems where we have some, well, let's say useful problems to solve. So I've mentioned already some of them, right? I've talked about fire extinguishers, I've talked about filling and emptying a propane tank. What's unique about those is that they have only a single inlet or a single exit. And what we can do is we can take a look at the equation above, then just modify it based on this special case of a single inlet or exit, plus some other simplifications. And you'll see that by the time I'm done with all this, we're going to get rid of this lengthy equation, and it will be replaced by something that's a lot more, let's just call it user-friendly. So what do we want to do then? Let's look at the special case. And the special case is where we have either a single inlet or exit, not both at the same time. It's either one or the other. And let's note that some further simplifications we're going to make is that we're going to neglect all kinetic energy change and potential energy change terms. Okay. For these types of problems, when we're filling or emptying a vessel, the speeds are going to be low. Not only is there going to be a low speed associated with what we're filling or emptying, but then there's going to be essentially no velocity associated with what's inside that particular container. And there's not going to be any height change associated with either of these processes. I mean, the exit is where the exit is. The entrance is where the entrance is. The tank sits where the tank does. So there's no potential energy changes either. And if we look only at a single in or out at a time, then we have a great simplification. So let's look at the case of first the single input. So let's say we're filling up our fire extinguisher. Well, let's relate this to the general equation above. All right, so we go back to the general equation above, and I can't really fit everything here all at once. But note that, wow, 8 of the terms cancel out right away, right? We've got 4 kinetic energy terms, all the v squared over 2 terms, right? We also have 4 potential energy terms, so those all go away. And if we're dealing with only a single input, then the entire exit stream goes away. There's hardly anything left for our equation, right? What we get is the following. We would get that the heat transfer minus the work. I'm just moving the work term from a positive on the right-hand side over as a negative on the left-hand side. And then we have our inlet flow path, but only the enthalpy, right? There's no kinetic potential energy. So, and there's only one of them, right? We can drop the summation. We end up with just MIHI, and then plus M2U2 minus M1U1. Absolutely everything goes. Absolutely everything else goes away, right? So this is the first law for a uniform flow problem where there's only a single input. I will note that when we solve problems involving uniform flow, we still have to solve a continuity equation simultaneously. If you go back to the continuity equation and get rid of the term that deals with the exit, this obviously is the first law. But if we look at the continuity equation, then the continuity equation really is also pretty simple, right? It basically tells me that the mass that flows in is just the difference between what we end with and what we start with. I mean, you don't even have to know that's called the continuity equation. You just have to use common sense, right? What flows in is the difference between the final and the initial. I mean, that should make sense. You can go back to the continuity equation and get rid of the summation signs and note that whatever mass is accumulating is only accumulating based on the difference between what flows in and out. So that's going to have to be used simultaneously. Good question. Yeah, it should be negative MIHI. Oh, I didn't put the minus sign there. You're right, because I had it as a positive on the left-hand side, so as I moved it to the right-hand side, it would have to be negative. So that's a good observation. That's my little typo. So yeah, I'll put a minus sign in here to make sure that we've done it correctly. So thank you for that. Anyway, so these are the equations we've used for a single input, and then we have equally simple equations if we have a single exit. And again, only a single exit, there's no inlets at the same time. So we go back up to our equation for the first law, and we still have our heat transfer minus the work. Again, the work moves over to the left-hand side. And then on the right-hand side, well, we have our M2U2, and then minus M1U1. Again, all the kinetic and potential energy terms go away, all the inlet terms go away since there's only a single exit. And then the last term on the right-hand side will be the exit term, MDHE. So plus MDHE, and the sign, I think, is correct here. This should be positive. So this is the first law equation that we're going to use. And then we'll have to look at the continuity. But again, we can go to the continuity equation, or we can just use our logic. If we're only leaving, that is, if we only have some mass flowing out, the mass that flows out had better be the difference between what we start with and what we end with. I mean, where else is it going, right? So clearly, this is just M1 minus M2. Now again, you can go back to the continuity equation and derive this, or you can just use logic and say, well, obviously, what's flowing out has to have started on the inside. The difference between what you start with and end with, M1 minus M2, and better equal what's flowing out, MP. So these are the equations, the two that are underlined, that you would have to use for either the charging or discharging problem. You can see that the one that's a single input isn't that charging? When we're charging the fire extinguisher or we're charging our propane tank, we're filling it up. So single input, these are the charging problems. And the single exit, this is when we're discharging something in the vessel, so these are the discharging problems. Thinking of them as filling or emptying a vessel, charging or discharging, single in, single out. I mean, think of them however you want, but these are the types of problems that we're looking at now. Now, there's no more theory to talk about. Really, I think all I need to do is go through an example problem to help illustrate how one solves these kinds of problems. So, are there any questions at this point with the theory? All right, so the example problem that we are going to do is problem 125 from chapter 8. So it's on the computer, and let's get that switched over. Thank you. Okay, so this one is from the 8th edition of your book. And again, all this is on Blackboard now, so I'm certainly welcome to allow your smart devices and read it directly. But let me read it to you anyway, not everybody has these. So, it says that we have a 0.3 cubic meter rigid tank that contains R134A at 14 degrees Celsius. At this state, 55% is in the vapor phase, in other words, that's the quality, and the rest is in the liquid phase. Obviously, what else would it be, right? It says the tank is connected by a valve to a supply line where refrigerant at 1.4 megapascals and 100 degrees Celsius flows steadily. It says the valve is now open slightly and the refrigerant is allowed to enter the tank. When the pressure reaches 1 megapascal, all the refrigerant in the tank is in the vapor phase only. In other words, you finally have turned that two-phase mixture into just all vapor, which is saturated vapor. And that's when the valve is closed and the problem ends. So it wants us to find the final temperature in the tank, the mass of the refrigerant that has entered the tank, and Q, the heat transfer between the tank and its surroundings. So let us start this one with the usual drawing. All right, so we have a tank, but what's different about this tank is that it's connected to a supply line. And they give me all sorts of information, so they do tell me the volume and it's rigid. So this is common. Most of these problems will be rigid tanks, but you know, I've seen problems where they're not rigid, where perhaps you have a piston cylinder device and you'd have to include some sort of boundary work, but most of the time they're rigid. So it tells me that the volume is 0.3 cubic meters. It's refrigerant 134A. It gives me the initial temperature, so Q1 is 14 Celsius, and the quality of 1 is 55%. It says that the supply line, and that's up here at the top, so the supply line has an inlet pressure of 1.4 megapascal, and an inlet temperature, 100. Now it says that the refrigerant flows steadily in the supply line, and that's really just the author's way of saying that there's no change in the inlet conditions. But frankly, all these uniform flow problems, we're assuming that the inlet conditions are uniform or the exit conditions are uniform, that there's no change in them. The author didn't really have to tell us that, but it doesn't hurt, I guess, to hear it. It says the valve is open, the refrigerant is entering the tank, and when we finally get to a final pressure of 1 megapascal, all the refrigerant is in the vapor phase only. So 0.2 is saturated vapor. And they would like us to find the final temperature and mass that's entering, so Fi, and then the heat transfer Q12. Now, you know, I call it Q12. Perhaps I should just be consistent and call it CV. But this is the heat transfer to the control volume during this particular process. All right, so I suppose we have to ask ourselves now, how do we even solve this problem? Well, this is clearly a charging problem. and there's just a single inlet. So it's pretty clear what the version is of the first law that we're going to have to solve for. Well, it's the one that's written above. So basically, heat transfer minus work is going to equal the negative m on hi and m2u2 minus m1u. Right, so this is a version of the first law that we're going to be utilizing. And of course, we're also going to have to use continuity. So again, whatever flows in, it's just a difference between what we end with and what we start with. So we have that. Now, do we have the ability to solve for anything up here yet? Well, yes. First of all, you might notice that we know the initial and final mass as long as we know the volume and the initial and final state. And we do know the initial and final state, right? We have the temperature and the quality initially, so that would allow me to find the initial specific volume. And we know the pressure and that it's a saturated vapor at the final state. So we should be able to look into our property tables and find the final specific volume, and we know that the initial mass is just the volume over the initial specific volume. And we know that the final mass, since it's a rigid tank, is that same volume but now divided by the final specific volume. So that's something very common for these type of problems, just to find this relationship between volume and specific volume in order to get the mass. But we do this not to get the inlet mass, right? We do it to get the initial mass or the final mass. You have to take the difference between the two in the continuity equation to solve for the inlet mass. But nonetheless, at least we see that we can find all this. So let me start putting little check marks here. I know the volume, and I know the initial and final state within the control volume, so I know the specific volume. So yes, I can find M1 and M2. And if I have M1 and M2, by the way, these are not dots that are going above. These are just my little check marks, and I guess this is the downside if I use a different technique. Anyway, these are my check marks. So we know the inlet mass. Okay, so let's just check off inlet mass. By the way, it's a rigid vessel. There's no work associated with it. There's no mixing devices. There's nothing, so we can always just put a 0 there on the work term. And again, getting back to what we were talking about a moment ago, we know our initial state, so we can certainly find U1. We know our final state, so we can certainly find U2. We know our inlet state, both pressure and temperature, so we can certainly find HI. And as we just mentioned a moment ago, we know M1, we know M2, we know MI. There's nothing left to solve for but the heat transfer, right? So if we're trying to solve for the heat transfer, it's really just a matter of finding the specific volume and enthalpy and entropy data, enthalpy and internal energy data we need. We can now plug it into all three of the equations that are shown down here at the bottom, and we can get all the results we're looking for. By the way, as far as T2, I don't know, that's really kind of a chapter 2 or 3 problem, isn't it? If it's a saturated vapor at a particular pressure, the temperature is obviously just a saturation temperature, right? So I don't know why they bothered to ask us that, but what the heck, that's fine. So any questions then? Let's just keep in mind that as we're talking about the refrigerant, all of our data is going to come from -11, 12, and 13, just depending on what the state is. So let's just go ahead and solve this problem. And we'll start by throwing together property data. So at T1 and quality at 1, it's a two-phase mixture. We know that we have to use table K11 for two-phase mixtures when we're given temperature. So we just go down to the 14-degree line. I don't know that I need to take the property tables and put them up here. I know this needs a statement up here. But we know how to do this. We've done it many times. So we're looking for two things, right? We need the internal energy at 1, and we also need a specific volume so we can find the mass. So V1 is dF plus quality at 1 dFg. So we go into our tables, we find that dF at 14 degrees Celsius is 0.0008018. And then loss of equality. And then VFG is just VG by VF. So 0.04347 is VG. And again, 0.00018 is VF. And if you go through the math, we end up with 0.02427 cubic meters per gram. So there's V1. To find U1, we do exactly the same thing. So that's UF plus volume of 1 times UFG. And so again, it's just a matter of pulling the numbers out of the table. 70.56 is UF. There's our quality. 167.3 is our UFG. And our math gives me 162.57 kilojoules per kilogram. And that is our thermal energy point. As long as we have it, we might as well find the mass. So M1 is the volume, 0.3 cubic meters, so the specific volume above. And we go through our math and find out. By the way, again, this is kind of sloppy because we can pick pen, but V1 is just so directly above. Nonetheless, we get mass number 12.36 kilograms. Now let's move on to state point 2. We're doing much the same thing, although state point 2 is a saturated vapor. So here at P2, sat vapor. Now we have to go into table A12, the saturation pressure table. V2 is equal to Vg, atmos pressure of 1 megapascal, which is 0.02033. And U2 is Ug, so Ug is 250.71 kilojoules per kilogram. And as long as we have the specific volume data, we may as well find final mass. So 0.3 divided by 0.02033. You can see the units work out properly. We'll get M2 is 14.76 kilograms. And last but not least, let's find our enthalpy at the inlet. So at PI, TI, well, here you can do your test. You'll see that this is indeed a superheated vapor. So we go to table A13, we go to the 1.4 megapascal subtable, we read down to the 100 degrees Celsius line. I mean, again, we've done this many times before, and we just pull out the value. We get the enthalpy of the inlet is 330.32. Next, we may as well find M2. I'm sorry, M the inlet. So MI, this is the difference between M2 and M1. So if we do that, we get 2.40 kilograms. There's the inlet mass. One of the things we're looking for. We've also been asked to find the temperature of point 2. I mean, honestly, I should have done that above, right? As long as I was already in the saturation table up here at state point 2, I should have found it there. So I'm just going to go back up. T2 clearly is Tsat at this particular pressure of 1 megapascal. So we just read that right out of the table. It's 39.4 degrees Celsius. That's known. And then the last thing we need to do is solve the first law and find our unknown heat transfer. So from the first law, heat transfer equals Now, this is written into your notes above. If I had a big blackboard here, I'd just put a big arrow across half the board, but, we're just going up to the first law, right? Look at the first law. Solving it down here again. I'm not going to rewrite it, I'll just throw in the numbers. So we have the negative of 2.40 kilograms. And in fact, I don't know, these are pretty straightforward. Maybe in the interest of saving time, I'll just let you plug away yourselves. So I'll just put et cetera, et cetera. If you go through the mathematics, you end up with 899 liters. And you will find that this is a positive number. If you go through the mathematics, it's positive. So heat is actually being added to the system in this particular case. So are there any questions as to the nature of this particular problem? Hopefully you don't mind that I didn't actually plug away with all the numbers here at the end. You've got all the numbers down in your notes, and you should be able to do it yourself pretty easily. I will be doing this a lot more as we progress through the class. I'd like to show you, about units and conversion factors and all that, but we've seen most of that already, so I'm generally just going to try to save time now and not go through each and every step. But I went through all the important steps clearly. Was there a question?
Yeah, so how are you differentiating between what you're finding at the subscript I for the inlet and versus 1 or 2?
Well, let me just pull this down. We have a tank which is connected by a valve to a supply line. So the supply line is your inlet conditions. So those are going to always be the same, and that's your I. But what's in the tank is different, right? I mean, we're starting with something at a markedly lower temperature and certainly not all vapor, it's a two-phase mixture. Those are your initial conditions. And then as you open that valve and you fill up whatever's in that tank, eventually you get to these final conditions of 1 megapascals of saturated vapor. So those are your final conditions. So there shouldn't be any confusion between what represents the inlet and what represents the initial and final state within the control volume itself. The inlet is not within the control volume. The inlet is just a pipe that's connected to it to provide whatever substance needs to be put in. But it's not the inlet, it's not the exit, it's the same substance, but it's had its own unique thermodynamic property, thermodynamic state with its own properties. So yeah, make sure you read whatever problems you're looking at clearly and make sure you know the difference between the inlet conditions and the initial and final conditions. One thing I also wanted to comment on, if we have a problem that involves an exit, sometimes those problems are a little bit confusing. For instance, let's say we started with a two-phase mixture and we had an exit pipe in the bottom of that tank. Well, if you have a two-phase mixture, because of the higher density of the liquid portion of the two-phase mixture, the liquid is always going to sit at the bottom of that tank. And if you have a valve on the bottom of the tank, then you're actually only allowing the saturated liquid portion of the two-phase mixture to exit. On the other hand, if you have exactly the same problem with the two-phase mixture, but your valve is on the top, well, again, the density difference between the saturated liquid and saturated vapor portion of the mixture is such that the vapor is going to always rise to the top. So if your valve's on the top, then it's only the saturated vapor that's going to be leaving. So when you look at problems that involve discharging, for many of those problems, you'll have to pay close attention to where it's discharging. Are you actually pulling the saturated liquid portion off the bottom, or are you pulling the saturated vapor portion off the top? So again, that's just a hint for some of the homework you will be looking at this week. Anyway, any other problems, any other questions on this problem or on uniform flow at all? Because this is really where we end chapter 5.
So is it always going to be the same substance? Either like...
Oh, absolutely. Right. These are still all pure substance problems. It's going to be water or a refrigerant or a gas. There's never going to be any always pure substance. Any other questions? All right. Well, then let us move on to chapter 6. This is everybody's favorite is the second law of thermodynamics. I think the first thing that I want to say is that this material can be quite confusing, and it gets even more confusing as we start talking about entropy over the next few weeks. If you're not showing up to class, and you're not hearing the lectures, and you're not hearing my take on the whole idea of the second law and entropy, then you're really doing yourself a disservice. Most students who just rely on reading the textbook are generally just not able to get it entirely. The second law doesn't have to be complicated, and hopefully you'll see as I present it that we're going to use the second law in a very specific way for very specific types of problems. But still, you do need to show up to class on a regular basis. So if you're not here today, well, then I'm talking to the wrong people. But if you're not going to be showing up to certain classes in the next couple of weeks, make sure you get the notes from somebody. Make sure you understand the notes. If you need to, come in my office and ask me to interpret those notes for you so that nobody's left behind. So, the second law of thermodynamics. Well, first of all, the second law is only around because of the first law. The first law tells us that for any process, energy must be conserved. But it really doesn't give us any restrictions. It just tells us that as long as we can keep track of all the energy flow paths, then theoretically that process is possible. But that's not really true. I mean, for instance, let me just give you an example or two. Let's say we have a, I don't know, some substance, gas maybe, and let's say we put some sort of a mixing device and we add a lot of work, a lot of mechanical work, we add energy input. As we're adding energy input, it's very likely that that gas is going to heat up. Now, that can happen, but can we reverse that process? Can we take a gas that has a mixer in it, can we cool that gas, and will that start the mixer into rotation? I don't think so. But the first law doesn't tell us that that can't happen. The first law just tells us that as long as the energies all work out, as long as we have the same amount of work energy coming in, and that equals the amount of heat that's being transferred, then the first law works out just fine. But we know that it can't happen, right? We base it on our observations. We know that just because the first law says something could happen doesn't mean it can actually happen in the real world, and that's really what the second law is all about. The second law provides us restrictions, if you will, as to the nature of certain processes. It basically tells us which direction processes can occur in. Right? So we need the second law. You know, just because we can solve something using the first law doesn't mean it's going to work. So that's what the nature of the second law is. That doesn't tell you how to use the second law. I'm just telling you what the second law is all about. Okay? So again, the second law basically tells us what direction certain processes are capable of occurring in. So, you know, this law gives us, this is called restrictions. As to what processes could occur. Some people like to think of these as what direction it can occur in, but we know that not everything can happen. So that's what the second law is about. Another good example is heat transfer from something cold to something hot. We know that heat is only transferred from the hot thing to the cold thing, but there's nothing in the first law that says that that has to happen. Right? The first law just tells us that as long as the heat transfer and the work and the energy change all balance, why can't you transfer heat from something that's cold to something hot? But we know that that can't happen, right? We know that if you take a hot thing and touch it up to a cold thing, the heat is always going to go into the cold thing, right? The cold thing slowly gets warmer, the hot thing slowly gets cooler. Can you touch a hot thing next to a cold thing and watch the hot thing getting hotter and the cold thing getting colder? Well, why not? The first law doesn't say you can't do that, but we can't do that. We know that that's not the way the world works. So that's what the second law is all about. It's nothing more complicated than that. Well, it is, because you have to use it, and mathematics is a little complicated. But in essence, that's the second law. Now, what is typically done, what I'm going to do here is give you two examples of systems which pretty clearly illustrate the need for the second law. So, two processes to illustrate. So, one of those processes is what we're going to call the heat engine, and the other of those processes we're going to call a refrigeration cycle. Now, quite frankly, the heat engine is a cycle. Sometimes it's also just called the heat engine cycle. But these are two different types of processes that I want to use to illustrate the need for the cycle. And we'll just go through them one at a time. And the first one that we'll talk about is going to be the heat engine. So let me make a sketch of the heat engine. So there's my heat engine. And the way heat engine works is we have to have some heat source and if you provide a heat source, then we should be able to do a certain amount of network output. Now, there's many devices that do this. I mean, like your automobile engine is one. You burn fuel to create the heat, and that does work. Okay? A steam power plant is another one. You burn fuel to create heat. You turn water into steam. You let that steam run through a steam turbine, and that rotates and generates work. So we know that this is not exactly wrong, but it's also not complete. Anybody who's ever worked with any of these heat engines knows that the only way for you to turn heat energy into work energy is to simultaneously reject some heat by the system. Okay, why are power plants always situated on big bodies of water, like an ocean or a lake, or why do they have that big tall tower called a cooling tower? They need to reject heat somehow. What about your engine? There's a radiator, right? Even if you don't have a water-cooled engine, like if you have a motorcycle or maybe an old VW Bug, something like that, you still have heat rejected. You just have what are called fins, basically metal protrusions on the side of the engine to facilitate heat transfer. But you have to have a way to reject heat. If you don't believe me, then just go in your car, drain your radiator, and then drive your car around for a while, and you'll see what happens. It'll work for a while until the engine seizes up and you pretty much have to throw away your car. You don't want that, but you're engineers, you know that you need to reject heat, right? This is just common sense. This is based on observation that you can't just turn heat into work, you also have to reject heat. That is what our experience shows us, right? To produce work, we must be able to extract heat from one source and reject heat to a heat sink, right? That's what our experience tells us. Nobody's ever been able to observe anything different, ever, right? So that's an illustration of the heat engine and what our experience tells us, right? So our experience says, and when I say our experience, I'm talking about collective experience from engineers based on observation and experimentation. But our experience says that to produce work, we must extract heat from a source and reject heat to what we call a sink. We can call it heat source and heat sink. That would also be more appropriate. So this is just an example of a heat engine, and again, this illustrates the absolute need for the second law of thermodynamics. Right? The first law says that we can turn heat into work all day long. It doesn't say anything about rejecting heat, but we know in the real world that we have to reject heat. So we got to use the second law. The second law will allow us to determine whether the heat engine that we're analyzing will indeed work properly. Okay, let's look at the other process to illustrate, and this would be the refrigeration cycle. And in the refrigeration cycle, again, let me give you an illustration. What a refrigeration cycle does is we extract heat from a low temperature heat source. So heat source at low temperature. And we reject heat into a higher temperature heat sink. So here's our heat sink. And this is at high temperature. Now, if you think about a refrigeration cycle, I'm talking about things like an air conditioning system, a refrigerator, a freezer, and this is exactly what they do, right? Let's just look at the refrigerator. The refrigerator, you want to run at about, 35 degrees Fahrenheit, yet the kitchen is going to be at maybe 65 or 70 degrees Fahrenheit. You are actually taking heat out of the food in order to keep it cold, but you have to reject that heat somewhere, right? You reject that heat out into the kitchen, and that's okay, right? I mean, you've all stood there in your bare toes in front of the refrigerator, and you feel that warm air kind of blowing on your toes, or maybe you feel the top or the back or the sides of the refrigerator, and it's warm, right? It's warm because the refrigerator is taking heat out of the cold food and rejecting it into the warmer outside air. But we know, again, based on observation, that the real world doesn't work that way. If you could simply pull heat out of something cold and send it into something hot, well, you just invented a perpetual motion machine of a type, and we won't get into that right now, but you know that it just doesn't work, right? Again, if you take a cold thing next to a hot thing, you're never going to make the hot thing hotter and the cold thing colder, which is exactly what would happen if you're taking heat out of the cold thing and putting it into the hot thing, yet somehow the refrigerator would work. Well, because we have to provide work input, right? Within that refrigerator is the refrigeration cycle. We're actually taking heat out of something cold, we're then doing work to it, so there's always going to be some sort of work input. Okay. And it's that work input then allows us to transfer heat from the cold source to the cold sink. So again, our experience tells us that the only way you're going to transfer heat from a cold thing to a hot thing is to provide work input. Now again, if you don't believe me, just go unplug your refrigerator at home and see how good your cold food is going to stay cold. Without the work input from the electric motor spinning a compressor, this will not work. So that's what our experience says, right? So our experience basically says that to extract heat from a cold source and reject it to a warm sink, we need to provide work. Cold source and reject it into a warm sink. And again, you can use the word heat source or heat sink if you prefer. You must provide work. Again, we need the second law, right? The first law doesn't help us out here. The first law doesn't care when we add work, as long as the amount of heat coming in from the source is somehow equivalent to the heat that's rejected to the sink, plus any energy change within the system itself. Then the first law tells us that that system should work just fine. But again, we know that it doesn't. So it's these observations and our inability to show otherwise that leads to the second law of thermodynamics. Whereas the first law of thermodynamics denies the possibility of creating or destroying energy, the second law denies the possibility of using energy in a particular way. So that's the relationship between the first law and the second law. Let me repeat that. It's these observations and our inability to show otherwise that leads to the second law. Whereas the first law denies the possibility of creating or destroying energy, right? It's conservation of energy. The second law denies the possibility of using energy in a particular way. Now, this is all our observations, right? Hopefully, you all accept these observations. If you don't accept the observations, well, you know, you're young, you're learning to be engineers, you'll have to accept them eventually. It's also good being an engineer because you don't always have to completely understand the theory. That's what physicists are for, right? We just have to know how to use the theory in order to create the machines to advance technology and better human life and all of that. I mean, that's really what engineering is all about. Some of you may not always have the mathematical skills or conceptual skills to fully understand the theory or the mathematical relationships, but don't let that get you down. I mean, you're an engineer. You have to accept things as being true. If you don't understand any of the theory that we're talking about from here on out, well, join the club. Most people don't understand the concept of entropy, but you have to know how to use the equations that will come from it. So that's what I'm going to emphasize in this class. So, two statements of the second law. So there's actually two common statements of the second law. The first one is called the Kelvin-Planck statement. And what the Kelvin-Planck statement says is this. It says, no process is possible whose sole result is absorption of heat from one reservoir and conversion of this heat to work. So the sole result is absorption of heat from one reservoir and converting this heat to work. Okay, that's the statement. What does that mean? Well, to us that means that in order for us to convert work to heat, we have to have a heat sink, right? So this basically tells us that we need a heat sink. This is the statement. The result is we need a heat sink. What's the other statement? The other statement of the second law is called the Clausius statement. And what the Clausius statement says is that no process is possible that results solely in the transfer of heat from a cold to a hot reservoir. Okay. In other words, we need work input. Right? We need work input. So we need work input, we need heat sink, as I stated above. Those are not part of the statement. That's just what we observe from this, right? We know from the Clausius statement that you can't just transfer heat from a cold to a hot thing. So isn't this Kelvin-Planck statement basically just giving us some restrictions on the heat engine? And isn't the Clausius statement really just the statement that gives us restrictions on a refrigeration cycle? So these two statements of the second law are exactly what we've been talking about before, right? This upper one refers to the heat engine, and this lower one refers to refrigeration. And my writing is too messy, I read it. This is heat engine, this is refrigeration cycle. All right, so what we really have to do now then is look inside the box. We can go back here to this basic box that is the refrigeration cycle, we go to this basic process heat engine cycle, and say, well, okay, how do we do this then? We know that we need to reject heat somehow. What device do we need? We know that we need to provide work input for the refrigeration cycle somehow. But what devices do we have inside the box? I'll give you a hint. These are cycles, right? These are both called cycles for a reason. We're going to start with a substance at a particular thermodynamic state, and then we're going to allow it to go through different processes until we get right back to the same state that we started with. So that's the next step, and I'm out of time. So we'll work on this more on Wednesday. So if this seems like we're kind of in the middle of something, then we are right in the middle of something. You probably don't want to start your homework yet dealing with this material. We just haven't gotten to that point. So anyway, I mean, you could start working on the homework that deals with uniform flow problems, but not the Chapter 6 material for sure.